In this presentation, we'll dive into the upcoming updates to the CFLib and client. We're making several changes that are aimed at improving the way we understand and troubleshoot communication links. We'll, of course, talk about the existing link quality metric and its limitations. And then we'll introduce several new metrics and these can hopefully help you optimize your communication setups and resolve, debug issues that you might have. And of course, we'll have a couple demo videos showcasing these new metrics. Note that these features are all under active development, so this is an ideal time to get in touch and share your input. Let's dive in. Let's start with the existing link metric, link quality. It's the only metric that we currently expose to the user, and it's been around for a long time. It's a value based on the number of retries it takes to receive an acknowledgement from the crazy fly that a packet was received. It's a percentage, and it's calculated as follows. We take 10 minus the number of retries, calculate a percentage based on this, and we average this over the last 100 packets, meaning that if on average it takes 0 retries to receive an acknowledgement, you get a link quality of 100%. If on average it takes a single retry, you get a link quality of 90%. And up to 3 retries, you get a link quality of 70%. And we retry for a maximum of 3 times per packet. Due to the nature of packet loss, what often happens is that you either lose all or none of your packets, however. So we think this is because you're either above or below the noise floor, and there's not much in between. Combine this with the way we calculate the link quality, and from the user perspective, what it usually looks like is either you get 100% link quality or 0% when you start losing all the packets. So in order to get more insights about your communication link, we're introducing several new metrics. Starting with latency, then packet rate, congestion, and RSSI. And I'll dive into these one by one, and then we'll watch 2 demonstration videos showcasing these. So latency. The latency we're calculating in the update is full link latency, including the time through the lib and a round trip from the PC to the crazy fly and back. And we're showing the P95 latency, 95th percentile latency, meaning that 95% of the latency measurements are below this latency number that you'll see, and 5% of the measurements are above it. This is an industry standard that we're following. So in order to implement this, we exploit the echo channel. It's an existing CRTP channel. It's basically made for a case like this, where you want to send a packet and receive the same contents back. So simply what we do is we take a timestamp, we send it on the echo channel, we receive it back, and we calculate the time difference between the current time and the timestamp in the packet. This latency metric applies to both USB and radio link, and it can be useful for debugging, ensuring real-time responsiveness, and finding the source of delays, or identifying network or processing bottlenecks. The next 2 metrics are only available on the radio link. We'll start with packet rate. It's simply the number of packets sent or received per second. This can be useful for debugging. It can help you make sure you have a consistent data flow, and a reduced packet rate can be an indication of interference. So like I said, we discern here between sent or received packets. Later on, we'll be calling this uplink. So from the PC to the Crazyflie, and downlink from the Crazyflie to the PC. Since downlink is implemented in the acknowledgement part, this basically means that the packet rates up and downlink are identical, except for when the Crazyflie does not receive and thus does not acknowledge. We think that it is actually the packet rate and not necessarily the bandwidth that is limiting our communications right now. So switching the radios between transmitting and receiving, switching channels if you're doing swarming, plus USB delays on the PC side introduce a lot of blank space. So if you look at the image at the bottom, you'll see that there's a lot of white space, but actually this is not to scale. We spend about 5 times more in the switching phase than actually receiving and transmitting. The USB delays is actually something we're looking into right now. This is actually, so since the packet rate is kind of limiting, the next metric is actually more interesting to look at right now. It's congestion. Congestion indicates how occupied the communication link is. So we use null packets for this. These are not new, they've been around. They are sent whenever we don't have any real data to send. And by measuring the ratio between these null packets and the total packets, we get an indication of how occupied the link is. So this can help users determine whether the link can handle more data or if they should reduce activities like logging to avoid congestion. And this can also be very interesting for use cases where you're streaming a lot of data. So like doing a lot of logging or using motion capture, for example. Because this metric is actually more about occupancy than congestion, it's actually about preventing congestion. We're still open to renaming this to something else. Next metric is received signal strength indicator, RSSI. This is a metric that measures the quality of the radio signal reception, and thus it's only available on the radio link. It has already been available in a library example, but now we'll enable it by default and expose the data in the lib and client. RSSI can act as an early warning of communication issues before actual packet loss occurs. And currently, this is only implemented on the Crazyflie side, so uplink. Now, before we dive into the demo videos, I'd like to show you the work in progress UI we have in the client so that you know what to look at. So in the top right, you'll find several new metrics. So from left to right, you'll find the familiar link quality statistic, then to the right, latency. And now we get into some kind of table. Again, it's a work in progress where we discern between down and uplink. We get our uplink RSSI, and then for both up and downlink, packet rate and congestion. So in the first demo, I'll be enabling more and more log blocks in the client, and you can see how the congestion increases. And then later I'll turn on my controller, and you'll see that the uplink congestion increases. So congestion is pretty low, and I'm enabling log blocks here, and you'll see that this downlink congestion increases. And next I grab the controller, turn it on, it's connected, and the uplink congestion increases to about 10%. So I'll just play it again because it's pretty quick. Congestion is very low. And I'm enabling log blocks. Downlink congestion increases because we're streaming more data from the Crazyflie down to the PC. I turn on the controller and the uplink congestion increases to about 10%. All right, next demo. So in this demo, I grab a Crazyflie and I move it into another room while leaving the laptop with the Crazy Radio behind. And yeah, this room is separated from the previous one by a thick concrete wall and a metal door. And you'll see, especially as I close the door, that the RSSI drops and the latency increases. And do note how the link quality remains 100% throughout. So, away latency, 20 meg, minus 40 dBm, or up minus 70, and latency up to above 40 milliseconds. So these are just some of the some examples of how these metrics are used. Well, of course, we have already been measuring a multitude of parameters throughout development and production. It has always been quite easy for us to lose track of the precise status of the communication stack. And that's why these metrics are already turning out useful for us internally. They've already given us some improved understanding. For example, on swarm latency. We already heard some reports of a problem with latency when swarming, so when using more than one Crazyflie per radio. And now that we can actually measure it and try to see how we can improve. Furthermore, we plan on integrating these metrics into our nightly testing. We've had, and we still have, some communication tests, but they're pretty crude, too crude to be really useful. Yeah, and we hope that with these new metrics, we can track trends over time, make sure that our code does not affect performance, set some baselines, and actually develop code that improves performance potentially. So you are all encouraged to try it out. There's a couple of draft PRs up on GitHub. If you want to try it out, you only really need the lib. But if you want to get the UI, get the client as well. And if you want to check out the latency, you'll need to recompile your NRF firmware with an additional C flag as shown below. So you're invited to share your experiences, thoughts on missing features, or suggestions for improvements. Note it's still a work in progress, especially naming is bound to change, like the occupancy or congestion I was talking about earlier. Also, you're welcome to share your thoughts about how to present these metrics in the client, in the UI. And again, here in the bottom, you can find the PRs on GitHub. So please head on over there, try it out, and hit us up and share your thoughts.